All right, continuing with our applications of derivatives to graphing. Section 4.4 is about concavity and big time graphing and curve sketching. So we know the first derivative contains information about where a function is increasing and decreasing. And we foreshadowed the ideas here when we looked at some examples and asked questions about more specific details of the shape of a curve. And those details were things that we can address with second derivative information. So this time, we'll look at the sign of the second derivative, and that'll give us some information, more subtle information though, about the shape of a graph. The second derivative is the rate of change of the first derivative. Derivatives are always rates of change. The first derivative gives a slope of a tangent line. So a positive second derivative indicates that the slope of the tangent line is increasing. So it's a little complicated. I'm not talking about direct properties of the graph, but about properties of tangent lines. A negative second derivative indicates that the slope of the tangent line is decreasing because second derivatives are rates of change of slopes of tangent lines. The book gives in their figure 4.24 here a graph of the function y equals x cubed, and let's magnify that. They're concentrating on the tangent lines. Now what happens as we move from left to right? What happens is, say at this particular x value where we have a tangent line, it has a very steep slope. We move over a little bit, draw a new tangent line, it has a less steep positive slope. Move over a little bit more, less steep, more. What happens is, as a little arrow indicates, these tangent lines sweep downward in this sense. Their slopes decrease. This end goes up, this end goes down, and the slope of the line decreases, as would be expected. And that's happening because of this particular shape of the y equals x cubed function. The fact that we're looking at an increasing function over here on the left would tell us that tangent lines will have positive slope. Yeah, but look what's happening as we move along this curve left to right. Tangent lines have less slope. Tangent line's very steep over here, less steep, less steep, less steep. We actually reach a horizontal tangent line with slope 0 there at the origin for this function. So this is an idea that we'll relate to called concave down, where we've got the tangent lines decreasing in slope. On the right-hand side, here, as x increases, now for x close to 0, we get positive slopes, but not very great, not very steep lines. And as we move to the right, we still have positive slopes, but now those slopes are greater. So as the arrow indicates here, we're getting increasing slopes of tangent lines. The second derivative then is going to be positive, is what it will amount to. And this is called concave up. So in both cases, we have an increasing function. Here we've got an increasing function that's called concave down. It's sort of arcing downward. And here we have a concave up function. It's increasing, but it's arcing upward in a sense. And we'll elaborate on these specific shapes here shortly. So with this idea of changing slopes of tangent lines, we'll define concave up and concave down more formally. The graph of a differentiable function y equals f of x is concave up on an interval I if y prime is increasing on I. Concave down on an open interval I if y prime is decreasing on that interval. And the term convex is used sometimes. We won't use the word convex. I don't think it'll pop up again in calculus. You may well see it in other math classes. But we'll stick with the terminology of concave up and concave down. by the first derivative test for increasing and decreasing functions. And this was exactly something increasing and something decreasing. The something itself was a derivative. Well, the first derivative test tells us if a derivative is positive, then the thing is increasing. If a derivative is negative, then the corresponding thing is decreasing. So here, the thing we're interested in is y prime. Its rate of change would be y double prime, or f double prime if I use that notation. So we see that we can relate concavity to the sine, S-I-G-N sine, not trig sine, the sine of the second derivative of the function. And there's your little emojis to remember what this theorem says. Let y equal f of x be twice differentiable on an interval I. If the second derivative is positive on that interval, the graph of the function is concave up. If the second derivative is negative on that interval, then the graph is concave down. So mechanically, when we actually do some of these, we'll be just like dealing with the first derivative, except we'll deal with the second derivative. So we'll find places where the second derivative is 0 or undefined, the second derivative. Such points for the first derivative were called critical points. So we'll find kind of like critical points for the second derivative. We'll partition the domain of the function up. We'll make a table. We'll pick test values. That'll give us signs of second derivatives, and that'll give us concavity information. So mechanically, very similar to what we did in the previous section. Only big difference is a function we'll use this time is f double prime, and in the last section it was f prime, and the conclusions will relate to concavity. Last time it related to increasing, decreasing. My patent pending here, concavity emojis tell you you're looking at a second derivative. There's two of these, positive, smiley face. This is concave up. Second derivative negative, concave down. So two plus or minus signs, second derivative, and a little smiley or frowny face indicating the type of concavity. The following is true. I don't think I saw a reference to it in the calculus book. This is a property of these concave things. If f is concave up at a particular point, then the tangent line to this function will lie below the graph of that function near the point x0, y0, where the function is concave up, where the second derivative is positive. If f is concave down at a point, then the tangent line must lie below the graph at a particular point. Point where the graph of a function has a tangent line and where the concavity changes is called a point of inflection. So I'd like to say the points of inflection are like critical points, except for the second derivative. Now, for some subtle reasons in their choice of words, they say the concavity has to change. So we won't know the points of inflection until after we've made a chart, a table of values. We'll have to refer to these interesting points as potential points of inflection. We'll look where the second derivative is 0 or the second derivative doesn't exist, and the graph of the function has a tangent line. So what we'll have to do is look at the second derivative, see where things go wrong, or where the second derivative is 0. Take the domain of the function, remove those points, and do a sign test. And that'll tell us about concavity. So let's do one of those, 4.4.2. Okay. They give us a function, f of x equals x to the 4th over 4 minus 2x squared plus 4. They say identify the inflection points and local max and local min of f, and identify the intervals on which the function is concave up and concave down. Okay, first let's differentiate it. Differentiate, bring the exponent down. They probably divided this by 4 to have us avoid fractions initially at least. Differentiate the 2x squared, we get a minus 4x. So here's what we get for f prime. Let's factor an x out. We're trying to factor it and find critical points. They ask us about maxes and mins, so that's overlaps with the previous section. Factor the x out. X squared minus 4 factors, 2x plus 2 times x minus 2. So the critical points are the points 0, -2, and 2. Well, -2, 0, and 2. Let's list them in order. These are the critical points because the derivative is 0 there. We could also have critical points where the derivative is undefined, but there aren't any of those. This is a polynomial for the derivative. The second derivative, let's differentiate this so we don't have to use the product rule. We'll get 3x squared minus 4, 3x squared minus 4. So we'll see where that doesn't exist. It exists everywhere. It's a polynomial, and where it's 0. So set this equal to 0, solve for x. We'll get plus or minus 2 over the square root of 3. If it changes concavity, then it's going to do it at these 2 points. Does it change concavity? I don't know. We'll have to make one of those tables and see. These, therefore, are potential points of inflection. A point of inflection is where the function actually changes concavity. Well, I don't know that it changes concavity at these points or not until I make a table. So that's why it's a little hard to see with these fonts, the italicized term potential points of inflection. Okay. As in the previous section, we're dealing with continuous functions. We're dealing with continuous derivatives. We're dealing with continuous second derivatives. Intermediate value theorem implies the only way, picking up here, the only way the second derivative can change sign as x increases is for it to pass through the value 0. We're dealing with continuous functions. The second derivative is continuous. It's a polynomial. I don't have those kinds of critical points where the second derivative is undefined. I'm sorry, I don't have those kind of potential points of inflection where the second derivative is undefined. But this is just our first example. Things will pick up. But the only 2 points of interest are -2 over the square root of 3 and +2 over the square root of 3. So we'll take the domain of the function, remove those 2 points, leaving us with these 3 intervals. So here's what we get for the 3 intervals. We'll, just like we did before, for those 3 intervals, take a test value. I've used -2, 0, and 2. Seems like I use -1 and 1, and those are easier points. These 2 points ring a bell, -2 and 2. These were, those were critical points. So I've actually plugged the critical points in to the second derivative. I've got my reasons for doing that. Granted, the arithmetic's probably a little bit easier with 1 instead of 2. The second derivative, here it is, 3x squared minus 4. So we'll plug -2, 0, and 2 into 3x squared minus 4. We get out these numbers here. We get a positive out at this point. The sign of the second derivative throughout each of these intervals is the same. That's the thing about the intermediate value theorem. So by choosing a test value and getting a positive number out, that tells me the function, the second derivative, is positive throughout that interval. Here we got a negative out. Second derivative is negative throughout this interval. Here we got a positive out. It's back to positive over here throughout the other interval. Positive derivative, think a little smiley emoji, concave up. Negative derivative, concave down. Positive derivative, concave up. So here's what we have for concavity. The second derivative test for concavity tells you positive second derivative leads to concave up, negative second derivative leads to concave down. But we'll make tables like this. It's the same mechanical technique we had in the previous section. So here's the information we had. So F does in fact change concavity in both of these points. So both of these points really are points of inflection. So at -2 over the square root of 3, the function changes concavity. At 2 over the square root of 3, positive, it changes concavity as well. We can find the corresponding y values. So we've evaluated f of plus or minus 2 over the square root of 3. It had only even exponents. Those plus or minuses get absorbed, and it looks like the value was 16/9 for what it's worth. Yeah, well, whatever. Unless I actually graph this thing, then it would be useful to have some points. We'll graph some soon, but not this first one. So the inflection points are these 2 points here. Here's where the function is concave up. Here's where the function is concave down, read from the table above. So just picking off for concave up the first and last intervals, center interval for concave down. The way we've defined concavity, I don't include the endpoints in this. The second derivative was 0 at these endpoints, and this is a little bit different. We defined concave up where the second derivative was positive, not where it's 0. So there's some subtle differences between how we treat intervals of concavity and intervals of increasing, decreasing, and it all follows from the definitions. They gave us the graph in terms of, I forgot, yeah, they gave us the original graph. And from that graph, we can see there was a minimum at 0, sorry, maximum at 0 and a minimum at -2 and 2. We found those to be the critical points. So, excuse me, let me go back and look at the graph. We had a minimum at 0, -2, and 2. We found those to be the critical points. So that must be where there's horizontal tangent lines. Going back to the first slide. Yeah, they gave us this graph. They didn't give us the X and Y values. Apparently we get 0 out. And algebraically, we see we do at 2 and -2. And at 0, we got out, what was it, 4? So local mins and a local maximum. Turns out we could use concavity as well to find those maxes and mins, as we'll see next. Okay, just as we use the first derivative to find local extrema, we can use second derivatives to find local extrema as well, sometimes. Now, the extrema will still occur at critical points. So the critical points, they'll still come from the first derivative. Theorem 4.5, second derivative test for local extrema says, suppose f double prime, second derivative of f, is continuous on an open interval that contains x equals c, apparently including c itself because it didn't say otherwise. If f prime of c equals 0 and f double prime of c is less than 0, then f has a local maximum at x equals c. All right, let's dissect this before we look at the other two. So f prime of c equals 0, that means horizontal tangent line. That means critical point. F double prime of c is less than 0. That means concave down. And their conclusion is local maximum, so critical point, concave down, local maximum. Let's go back and look at a picture. There's a good picture right there. Where's the critical point? That'd be right there at the top of the frown, where the tangent line is horizontal. We know the second derivative was negative, is what we were told in that case. That gives us the concave down stuff and gives us a local maximum. Second derivative negative, concave down, critical point, local maximum. Second derivative positive, here's the critical point at the bottom of the smiley face. Concave up, it's going to be a local minimum. And that should be part 2. Yeah, f prime is 0. Let's see, the second derivative is positive, so you're thinking smiley face now. And there's a low point on that smile where the function has a local minimum. If the second derivative is 0 and the first derivative is 0, so we're still looking at a critical point, then this test fails. The second derivative test for local extrema fails. The function may have a local maximum, it may have a local minimum, or it may have neither. So the first derivative test was a little bit more conclusive than the second derivative test. The second derivative test is maybe easier to check. I mean, you only have to check individual points in these first 2 cases. So when it works, the second derivative test is probably a little easier than the first derivative test. When it fails, I guess I'd be looking back at what information I can get from the first derivative test. Let's go through a proof of this. Oh, did I miss an example? Excuse me. Did I overlook an example? 1, 2, 12. Oops, I might have these out of order. Okay, sorry. Let's go through second derivative test proof, then we'll look at that example. Okay, so hypothesis of continuous second derivative, and then these three cases. Let's look at this one. If the second derivative is negative, then the second derivative is negative on some little open interval. They told us we have a continuous second derivative. If you're negative at some point, then nearby that point, that input, you're going to have negativity. This is illustrated in exercise 2.5.70, properties of continuous functions for the record. So we've got a negative second derivative on a little interval. Corollary 4.3, the fact that derivatives are rates of change and tell you about increasing, decreasing. I'm treating this as the derivative of the first derivative. So this derivative of the first derivative is negative, so that first derivative itself must be decreasing. The first derivative is decreasing because its derivative is negative. The second derivative is negative. So we have a decreasing f prime. F prime of c itself is 0, so the sign of f prime must change from positive to negative as x increases through the value of c. So I know we have a decreasing derivative. Here we've got a derivative of 0. It was decreasing, must have been positive to the left of there, left of c. At c we get out 0, and to the right of c we get out something negative. It's a decreasing derivative. So we've got that this is the derivative changes from positive to negative as x increases through this value. So f itself has a maximum, local maximum, at x equals c. That was a first derivative test for local extrema. It was stated in terms of f prime changing from positive to negative or from negative to positive. We went through that. Probably you think about it more in terms of the function increasing or decreasing. Hey, we've got f prime as positive to the left of c. That's an increasing function. It's negative to the right of c. That's a decreasing function. Okay, that's went uphill and then downhill. That's a local maximum. So if you think about it in terms of uphill and downhill, that's a little bit easier to remember than the way they stated it in terms of derivatives changing sign. But in the event that the second derivative is negative, we get this kind of behavior. Part 2, it'll be basically the same thing, except now we've got f prime is increasing because this time the derivative of f prime, f double prime, is positive. So f prime itself is increasing. We've hypothesized f prime of c is 0. Okay, then f prime must have increased through some negative values up to 0 at x equals c and continue to increase into positive values. That is, f prime changes from negative to positive as x increases through the value of c, and that corresponds to a local minimum. Those negative values of f prime before c would indicate that f is decreasing. At x equals c, it reached a minimum, and to the right of c, after c, the function increases. First derivative information. Easy enough to remember from the little smiley and frowny emojis, but here's the proof. In the third part, they say the test fails. All we got to do is find some examples that show it doesn't work in any particular way. Consider 3 functions. F sub 1 of x is x to the 4th, f sub 2 of x is negative x to the 4th, and f sub 3 of x is x cubed. I actually looked at a graph of that in the first figure. We have the derivative of all 3 of these at 0 is 0. 4x cubed, plug in 0, get out 0. Negative 4x cubed, plug in 0, get out 0. 3x squared, plug in x equals 0, get out 0. So 0 is a critical point for all of these. That's the value c addressed in the theorem. If we take the second derivative, Each of those involves an x, some multiple of x. This one's 3x squared, this one's negative 3x squared, and this one's 6x. They all involve x, a multiple of x, or a power of x. You plug in 0, you get out 0 for those as well. So these three functions satisfy both of these conditions, but they behave in different ways. X to the fourth has a local minimum at x equals 0. That shouldn't come as a surprise. Hey, x to the fourth is non-negative. It's positive except at 0 where it has a minimum. Negative x to the fourth, it's non-positive. It's negative everywhere except at 0 where it has a local maximum. And x cubed, as we saw in that figure earlier, has neither a max nor a min at x equals 0. It increases, levels off, and then increases some more. And we probably dealt with that in the past also. So there's a proof. Let's do this exercise. And now, let me back up through the exercise where we're given a function and asked to identify the coordinates of any local and absolute extreme points and inflection points and graph it. Okay, so we're given a function as a product. I got two options here. I can product rule it. I can multiply it out. Let's just product rule it. I've got to factor it eventually, so maybe leaving it as a product will save a little bit of trouble on factoring later. Product of two things. We've got derivative of the first, derivative of x is 1. A little square bracket notation, times the second, plus the first, times the derivative of the second, was chain rule. To differentiate 6 minus 2x squared, we'll bring the 2 down, rewrite the stuff inside, subtract 1 from the exponent, getting a 1. And then multiply by the derivative of the stuff inside. There's a little arrow saying the chain rule is spitting out the derivative of the stuff inside, which is negative 2. Yeah, I got a factor of 6 minus 2x in both of these. So let's bring that out. I mean, it's going to become a goal of factoring because I'm looking for critical points where the derivative is 0. Factor 6 minus 2x out of this first term, you're left with a 6 minus 2x because it was squared in the expression. Factor 6 minus 2x out of this, and we're left with x times 2 times negative 2. That's negative 4x. So we got a minus 4x there. It factors like this. I didn't have to FOIL backwards because I didn't multiply out. If I had multiplied out and then found the derivative, I'd have to unwind all that stuff. So this is a slightly more complicated derivative, but easier factoring. And we got a 6 minus 2x minus 4x. That's a 6 minus 6x for that second term. So here's the derivative. We want to see where that derivative is 0 or undefined. Of course, it's a polynomial. It's defined everywhere. It's 0 when this term is 0. That happens when x equals 3. And it's 0 when this term is 0. That happens when x equals 1. So 1 and 3 are the critical points. Always write them in order. Right? I'm going to have to go down here to the domain of the function and remove these critical points if I check the first derivative. This is actually where I ask a question about points of inflection. So I will check the second derivative, but be careful to list these in order. We're going to make a chart out of them, but not for the first derivative, for the second derivative. So let's take the second derivative. Let's differentiate this version here. That'll take a product rule, but it's not complicated. Derivative of the first is negative 2. The second is 6 minus 6x. The first is 6 minus 2x. Derivative of the second is negative 6. Trust me on the arithmetic, it produces this. That is 0 at x equals 2. That's always defined. So x equals 2 is a potential point of inflection. Excellent, only have one. We'll make a table by taking the domain of the function, which is all real numbers, the whole real line, and remove x equals 2. Pop that out, leaves you with these two intervals. Take a test value. Let's use 1 and 3. Hey, those were the critical points. And substitute into the second derivative. We're testing the sign of the second derivative. Negative 48 plus 24 times 1 apparently leaves us with negative 24. And negative 48 plus 24 times 3 apparently leaves us with positive 24. That symmetry, I bet you, is not a coincidence. This is negative. When the second derivative is negative, think frowny face, we've got concave down. 24 is positive, think second derivative and smiley face, concave up. So here's where we've got concave up and concave down. We won't include the endpoints when writing it in terms of intervals. The function really did change concavity. It was one concavity on the left and another on the right. So it did change concavity. So 2 is not just a potential point of inflection. It is indeed a point of inflection. The book usually expresses the points of inflection in terms of the x's and the y's. The word point takes on a little ambiguous meaning in here. But I plugged 2 into the function. Looks like we get out 8. So the point of inflection is the point 2a. We'll graph that point. It's an important point. Now, what about extrema? Well, we saw 1 and 3 were critical points. We also saw that at 1 and at 3, we had certain concavities. We had at 1, we had concave down. Okay, concave down at a critical point, think frowny face, concave down, and the frown has a point at the top, a maximum point. At 3, we had the smiley face. 3 is where the critical point is. Got something that's concave up. It'd be the bottom of the smiley face and would correspond to a min. So we have a maximum there, local maximum there, a local minimum there. That is, instead of smiley and frowny face, is something a little more professional. It's the second derivative test for local extrema. Theorem 4.5, parts 1 and 2. We went through the proof. So we have a maximum at 1 because of the frowny face stuff, local maximum, and a local minimum of 3 because of the little smiley face stuff. And that maximum is f of 1. It looks like it's 16. The minimum is f of 3, which looks like it's 0. They ask us explicitly in this one for the coordinates of the local max and the local min. So there they are written in terms of x and y. You really want to find the y coordinates? Yeah, I want to graph this thing using the fact that it contains this point, and this is the point of inflection. It contains this point, and this is a local maximum. It contains this point, and this is a local minimum. Okay. We're going to graph this thing. We're going to do so by using little red horizontal hash marks like we did in the previous section to indicate points where there's a horizontal tangent line where the derivative is 0. And this concavity stuff is pretty subtle. To draw emphasis to the fact that concavity has changed, I'm going to put a red X through each of the points of inflection on the graph. So first, plot the points. So first we'll plot the 3 points we know. I guess we'll find intercepts. That'll be part of our graphing procedure as well. The function, it was x times 6 minus 2x quantity squared. The function has intercepts of x equals 0 and x equals 3. I don't have a clear expression of the function in front of me. The y-intercept then is just 0, 0. So we'll plot these 2 intercepts. I think they ask about those, and the 3 points of interest, the max, the min, and the point of inflection. What's special about the point 2a? Ooh, it changes concavity there. What's special about the point 116? Derivative is 0. What's special about the point 30? Derivative is 0. So we'll plot these points, drawing attention to these 3 special points, and then we'll connect them respecting concavity. It was concave down on the left and concave up on the right. And all this information's in the notes. But pasting all this together, we had, here's an intercept, 0, 0. Here's an intercept, 3, 0. Here's a critical point, 116. Little hash mark to indicate it's a critical point where the derivative was 0. At 3, 0, we had a critical point. We claimed it was a local minimum. Derivative was 0, little red hash mark. And at 2, 8, from the previous slide, the function passes through this point and changes concavity. So what I'm going to do is put a red X to indicate that we've had changes of concavity in terms of you working them. Don't bother with colored pencils or anything. Just make sure you put little hash marks on these to show you know what happens there. And especially, please put a little X where the points of inflection are, because it's kind of hard to tell. This function's arching downward and then it changes to arching upward. It does it somewhere between up here and down here. It's not entirely easy to draw in such a way that you get it reflected to be right there. So I'll put a little X on there to draw attention to that. So we've got the points plotted. Now you wanted the function to pass through those points and be concave down. Okay, so it's concave down. It levels off because a little hash mark. It remains concave down, passes through this point. Now it starts to arch upward and becomes concave up. Levels off, little hash mark, moves on in this direction, remains concave up. How do you know this is a good graph? How do you know it doesn't, maybe it turns around, comes back down? How do you know it doesn't do that? It'd have to have another critical point. How do you know it doesn't have a horizontal asymptote somewhere out here from the information in front of you? Well, we could test for asymptotes. How do you know it doesn't maybe level off somewhere? Maybe it's got this line of text as an asymptote. How do you know it doesn't level off and do something like that? Do you know? You do know. If it did that, it'd have to change concavity. Have to be concave down to have a horizontal asymptote. And it's not. We know it's not. We know it's concave up from 2 to infinity. So this must be a pretty good graph of that function. They ask about they ask about absolute extremes as well. I don't think it's got any absolute extremes, right? These are local extremes. It gets less than 3 over here. I'm sure it gets greater than 16 somewhere over here. Absolute extreme points, it has none. I can tell that from the graph and the conversation we just had. Okay, and next we had that, so let's go ahead and get that out of the way. All right, so there's an example using concavity to graph. Comment, Theorem 4.5, this idea about maxes and mins based on concavity only applies to critical points where the derivative is 0. It doesn't apply to critical points where the derivative is undefined. If the derivative is undefined, the second derivative will certainly be undefined. We've got problems where it's inconclusive. That was part 3. Let's illustrate this in all its glory after making one more observation. Then we'll go through several examples. Okay. What we'll do next is combine first and second derivative information. Suppose we had a positive first derivative and a positive second derivative. Positive first derivative tells you increasing. Positive second derivative tells you concave up. Combine those two pieces of information, we must have that the graph looks something like this. It's the right-hand piece of the smiley face. Suppose we had negative first derivative and positive second derivative. Negative first derivative, decreasing. Positive second derivative, concave up, must look like this. It's the left-hand part of the smiley face. Increasing, concave down, related to the signs of f prime and f double prime is given. Increasing, concave down, arching downward, there you go. Decreasing, concave down, decreasing and concave down, looks like that. So in terms of first and second derivative information, we got 4 pieces that the function could look like. Now you have to stretch these some to get them to pass through the known points. But when we graph a curve, they'll be made out of these 4 types of shapes. Granted, they may have to be stretched some. I might even have to deal with some horizontal or vertical asymptotes. We will before this section is over with, so in that case it gets stretched a lot. But we'll still have these 4 fundamental shapes that make up the shapes of the graphs of the functions with which we deal. So let's look at 3 examples. Exercise 4.4.104 says, sketch a smooth connected curve y equals f of x with the following properties. Okay, good news, they gave you a bunch of stuff. We got to interpret that stuff, but we'll know a lot about this function. They've told us f of negative 2 equals 0, f of 0 equals 4, f of 2 equals 0. Okay, so that's 3 points on the graph of the function. So we'll probably start with that. They've told us f prime of x is greater than 0 for the absolute value of x greater than 2. F prime of 2 and f prime of negative 2 are 0, and f prime of x is less than 0 for the absolute value of x less than 2. Okay, that's the increasing decreasing information. 2 and negative 2 are critical points where the derivative is 0. Horizontal hash marks at 2 and negative 2. And they told us the value of the function at those two numbers as well, at 2 and negative 2. Derivative is greater than 0. This is positive derivative. This is an increasing function. So the function itself will be increasing for the absolute value of x greater than 2. We'll have to translate that into some x values. For the absolute value of x less than 2, derivative is negative. That means the function's decreasing. So that batch of information is increasing, decreasing information. Finally, here's some concavity information. The second derivative is negative for x negative, and the second derivative is positive for x positive. Instructions are as above. Indicate points where f prime is 0 with a hash marks, indicate points of inflection with x's, and graph it. All right. How about this? Let's take their information and turn it into a table. I want you thinking in terms of these kinds of tables. They told us, back up for just a sec, f prime of x is greater than 0 for the absolute value of x greater than 2. Absolute value of x greater than 2 is two things. Either x is greater than 2, in which case it's in this interval, or x is less than negative 2, in which case x is in that interval. So this condition corresponds to these x values in the interval notation. We reviewed that, and I think in Appendix A1, we talked about absolute values and inequalities. The derivative is negative for the absolute value of x less than 2. That means x is between negative 2 and 2 in this interval. Negative first derivative, decreasing. So f is decreasing here. Positive derivative here. Function's increasing here. About concavity, we've got negative second derivative when x is less than 0, when x is negative. So let's see there, we've got concave down, negative second derivative, concave down, frowny face. Second derivative positive when x is positive, concave up for those x values. So concave up on this interval, concave down on that interval. Here's your table. So here's a table that includes all the increasing, decreasing information. I took the domain of the function and removed the critical points, negative 2 and 2, and also removed 0 because the function changes, here it is, changes from concave down to concave up at 0. So 0 becomes an important point as well. I see that from the information they gave us, not from our computations. So I'll break up the domain into 4 pieces. We were told negative infinity to negative 2. We were told positive derivative and increasing. So we get increasing here. We were also told for x less than 0, here it is, for x less than 0, f prime of x is negative. Second derivative is negative here, well, and here as well. That means concave down. So the information described up here falls into this information in a table. It changes concavity here. Right, it went concave down, concave down, concave up, concave up. So it changed at 0. So 0f of 0, that is the point 0.04, they gave us that one as well, actually is a point of inflection. If I had computed it, it would have come out and I wouldn't have known it's a point of inflection until I make the table. But here they actually gave us concavity information, albeit indirectly. So we got a point of inflection. We got all this concavity information. That's a bunch of information. Recycling that information, here's what we had on the previous slide, the increasing, decreasing concavity information, along with the 3 points they gave us. All right, and in addition to that, we've got some information about little horizontal hash marks where the derivative was 0. So we'll plot the 3 points, -2, 8, 0, 4, 2, 0. So that gives us the 3 fat blue points. Tried to be consistent with my graphs. That comes first. Next, the red stuff. I know the function has a derivative of 0 at -2 because they told me so. A little horizontal hash mark. I know the function has a derivative of 0 at +2, a little horizontal hash mark. And we know up here from the table, and as commented on the previous slide, at 0, 4, it changes concavity, changes from concave down to concave up. So first I'd plot the 3 blue points. Second, I'd plot the information given in red. Third, I want a function that does this. So we got a bunch of information now. We've got increasing, decreasing information and concavity information. Okay, less than -2 over here. I want increasing, concave down, and leveling off here. Next, between -2 and 0, I want decreasing and concave down. So I got to connect this point to this point with that kind of thing. So I want decreasing and concave down. I reach this point. Now we're looking at an x value of 0 along the x-axis. Shifts over to decreasing and concave up. So it continues to decrease, changes over to concave up. Can you tell it changed from concave down to concave up from these points to these points? Well, yeah, the red arrow it indicates that. But that little subtle detail is kind of hard to see in a graph. That's why the red X's are helpful. So we get decreasing and concave up, levels off down here, and then it comes out of there increasing and concave up. So it comes out something like that. The graph of that function, it looks a lot like this. How do you know? It doesn't turn around and come back down. Well, that requires more critical points and a change in concavity. How do you know it doesn't have a maybe horizontal asymptote? That'll require a change in concavity that isn't there. How do you know it doesn't have a vertical asymptote? They told us it was defined everywhere, so it doesn't have vertical asymptotes. I think they told us a smooth curve defined on the real numbers. So it maybe doesn't have vertical asymptotes. If it did, we probably couldn't get it to satisfy all of this information as well. Yeah, it's this function is defined on the whole real line, no vertical asymptotes. So there's how to use increasing, decreasing, and concavity information all together on a not very complicated function. What function was this? You know, they didn't tell us. They told us the information, not the function. Let's do another one. Okay, here's a function. Do that same kind of stuff. Identify the coordinates of the extrema and the inflection points, graph it, use hash marks and X's. Okay, so I need to find the information like they gave us in the previous question. Let's take this function, cube root of x cubed plus 1, and write it as x cubed plus 1 to the 1/3 power, so it's easy to differentiate. We'll bring the exponent down, subtract 1 from the rewrite the inner stuff, subtract 1 from the exponent, 1/3 minus 1, -2/3. Oh, chain rule, composition of functions here. Chain rule will say, add on to that the derivative of x cubed plus 1, which is 3x squared. You want to simplify? And not really, but I have to, because I've got to find critical points. See, the 3 and the 1/3 cancel. That's nice. That leaves us with an x squared and an x cubed plus 1 to the -2/3. If you like, I can write it as a quotient. Let's go ahead and do that. What's going on with critical points? Here's the derivative. Is the derivative ever 0? Only time the derivative would be 0 is when the numerator is 0, and that occurs at x equals 0. How about undefined? Derivative ever undefined at points in the domain of the function? Yeah, that denominator could be 0 if x is -1. X equals -1 is a critical point because f prime is undefined at -1. So we've got two critical points, and for different reasons. X equals 0 is a critical point because the derivative is 0. I'll put a little horizontal hash mark there. F prime is undefined at x equals -1, so what are you going to do there? I'm going to put a little vertical hash mark to indicate something's wrong with the derivative. I don't know what unless I explore this more deeply. What's the domain of this function? I probably should have commented that originally. X can be anything. You can cube anything, you can add 1 to the result, and you can take the cube root of anything. You can take cube roots of negatives in particular. So there's no problems with input values. So the domain is all real numbers, by the way. Here's the first derivative information. So far, we'll make a table and consider more first derivative information. Next, second derivative. So we'll differentiate. How about this version? Let's differentiate this version or this version. Let's differentiate this version because that's what I typeset. That requires a product rule. If I differentiate this version, that requires a quotient rule. I'll end up needing a quotient anyhow. I don't know, maybe that's a better idea. Well, I've differentiated here the product. That'll be derivative of x squared, which is 2x, derivative of the first. Rewrite the second, plus the first, x squared, times the derivative of the second. Okay, we'll bring the exponent down, rewrite the inside, subtract 1 from the exponent, chain rule puts a 3x squared on here. Simplify, yeah, because I got to find potential points of inflection. Simplify, I leave it to you to pause the video and convince yourself I've gotten a correct common denominator in doing this addition and further simplifying. So the second derivative simplifies to this. All the details are spelled out there, but let's not spend our time on that. What's up with this? Is the second derivative ever 0 or undefined? Yeah, at x equals 0, the second derivative is 0, so x equals 0 is a potential point of inflection. How about at x equals -1? Because I still got a problem at -1. The second derivative is undefined. Yeah, so is the first derivative. Does that count as a potential point of inflection? Well, that's semantics more than anything. It's an important point, and the second derivative could well change sign there. Is it a point of inflection? We said points of inflection were where the second derivative, we said the points of inflection was where the function changes concavity. And we've observed that they were points where the graph of the function has a tangent line. Well, I don't want to get into this. We could, because we've looked at this in some of the exercises, I think it was. But we could show that y equals f of x. It has a, what's that say down there? A vertical tangent line at x equals -1. It does have a tangent line. It's a vertical tangent line, the slope of which is undefined. But the long and short of it is -1 is an important point. And it is a potential point of inflection if you read through the details and the verbiage closely. I'm a little bit bigger on ideas than the exact verbiage this book uses. 0 is important and -1 are important, just like we had for the first derivative. Okay, so let's take 0 and -1, remove them from the domain of the function. As observed earlier, the domain is the whole real line. So we'll take the whole real line, we'll remove -1 and 0, producing these three intervals. Pick a test value from each of these three intervals. Use nice, neat whole numbers. You're stuck having to use a fraction in this one. Plug into those test values, plug them into, call the test value k, plug them into the derivative, finding f prime of k, that'll be some number. That will tell me the sign, SIGN sign of f prime throughout that interval, as before. Take that test value, plug it into the second derivative. The sign of the output will tell you the sign of the second derivative, and that'll give you concavity information and increasing, decreasing information. Here's the derivative for reference. Here's the second derivative for reference. Let's check this first column. I plug in -2 into the derivative, so we'll have -2 squared divided by -2 cubed plus 1 2/3 power. And I put, as usual, what I substituted in, I put in parentheses so you can find it. Let's just worry about the signs. All that matters is a sign. I don't care what number this is. I just care whether it's a positive or negative number. That numerator, -2 squared, that's positive. Anything squared except for 0 is positive. We won't be getting zeros out. Those numbers are gone. They produce the zeros. -2 squared, positive. -2 cubed plus 1 to the 2/3 power. You see that 2 right there in that 2/3? That means take the cube root and square it. So we've got something squared in the numerator. We've got something squared ultimately in the denominator as well. Everything's positive. All those derivatives are going to be positive. All those first derivatives are positive because of all the 2's, because of up here, because of the fact you're squaring something in the numerator with that little 2 there, and you're squaring something in the denominator because of that little 2 in the numerator of the 2/3. You're doing some other stuff as well, but ultimately you're squaring. All right, well then we won't get negatives out of that, not in here. So all 3 of those derivatives are positive. And this function is increasing, increasing, and increasing because a derivative is always positive, except at the critical points. Second derivative, okay. Here I've got a 5/3. I'm not squaring anything in the denominator. I've also lost that squaring in the numerator. So this will be a little more interesting, I guess. Plug the -2 into the second derivative. Okay, I'll get 2 times -2 divided by -2 cubed plus 1 to the 5/3 power. So here that is. There's lots of 2's floating around. The ones in parentheses are negative, and they result from the function substitution. In the numerator, we get, well, negative something. Oh, it's -4 for you fans of numerals. In the denominator, we get -8 plus 1 is -7 to the 5/3 power. -7 to the 5/3 power is what? I don't know, it's negative. Because of the odd numbers. So I get a negative divided by a negative, which is positive. I'm not interested in this row, not the least bit interested in what these numerical values are, only whether they're positive or negative. This row, the f double prime of k, same thing. Not interested in the values, only the signs. So I'll save myself some headaches of arithmetic and just analyze the signs. We get, for the second derivative, positive, negative, and positive. Seeing that, the function really does change concavity at -1 and 0. So I think both of those are points of inflection. We'll say that at the bottom. It really did change sign. I'm sorry, the original function changed concavity at -1 and 0. So that yields 2 points of inflection. The points of inflection are given as XY values. Let's see. The function had a critical point at -1. The function increased, and then it increased some more. Increased, leveled off, and increased more. When we go from up to -1, I kind of view this as where -1 lives between these intervals. It went up to -1, and beyond that, it went up some more. It changed from increasing to, well, more increasing. It didn't change. That's not a local extrema. Over here at 0, same story. Increased up to whatever value it has at x equals 0, and it increased afterwards. This function's always increasing. It did level off in a couple of points, but this function's always increasing. So it doesn't have a max or a min. First derivative test justifies that. So no maxes, no mins, but some critical points of interest, and 2 points of inflection. In fact, the critical points and the points of inflection coincide. All right, so here's the information we have. A quick synopsis of it in terms of increasing, decreasing, concavity, critical points, and function values. We actually only have 2 points to plot. We could run find intercepts. Turns out we've already got the intercepts. Okay, so we'll plot those 2 points. At -1, we get out 0. At 0, we get out 1. So first I put down the 2 blue dots. We know the function changes concavity at -1 and at 0. So I'll put x's through those, changes concavity. We know at x equals 0, the derivative is 0, little horizontal hash mark there. And at -1, the derivative is undefined. So I'll tell you what I'm going to do. I'll put a little vertical hash mark there to indicate something goes wrong with the derivative. We claimed, but we didn't analyze exactly what's going on with that point where the derivative is undefined. Is it a cusp, a corner, a vertical tangent line? We claimed it was a vertical tangent line. And we could verify that with some limit stuff. So let's take that as given. Just put something there to indicate the derivative is messed up. And a vertical hash mark would be a good thing to put considering how we treat horizontal tangent lines. Then we want. So I'd have the first of 2 blue dots, then the information in red. We'd have this function increasing in concave up. Okay, do something like that. It passed through this point, I say, with a vertical tangent line. I haven't shown that, but that is the case. At least, for all I know, it could come up here and have a sharp point in it. That's possible. We didn't eliminate that possibility with what we computed. Here, it changes to concave down, remains increasing throughout. So I want increasing and concave down. It's well behaved over here. It levels off. And then it changes to increasing and concave up. So it must look something like that. The graph of this function must look a great deal like that. Could it have a horizontal asymptote? Not over here. If it had a horizontal asymptote, it'd have to arc over and level off, in a sense. And that would change the concavity. Could it have a horizontal asymptote over here? Actually, it could. It's got the right kind of concavity. It's possible that it has a horizontal asymptote. Would you believe it's got neither of those? It turns out it's got an oblique asymptote. This has an oblique asymptote of y equals x. I don't want to have to establish that. But if I draw the line very carefully, y equals x, this will asymptotically approach the line y equals x. And we mentioned oblique asymptotes in the past. But here's a graph. My interest in this particular graph is this satisfies all the information we did establish, right? Horizontal tangent line, right concavity, right increasing, decreasing, messed up derivative at -1. I messed it up by giving it a vertical tangent line in the picture. There's other ways to mess it up. All right, 54, we want to do this one as well or talk about something else. Let me check the notes real quick. Let's do this one as well. Okay, a function involving an exponential. Y equals x e to the negative x. Let's call it f of x. Do your thing. So do the same stuff again. Identify extreme points, points of inflection, graph it, use the hash marks in the x's. Okay, same protocol, function with an exponential in it this time. Take the derivative. Let's speed this up a little bit. Straightforward to take the derivative, you'll use a product rule. I see my square brackets with a picture of the product rule. Oop, there's a little chain rule. Yeah, when you differentiate the e to the negative x, that's a negative x function inside an exponential function. So it spits out a -1. Factor it to produce this. Okay, where is this 0 and where is this undefined? It's never 0. The exponential function is never 0. This factor is 0 when x equals 1. Also, the exponential function, it's always positive. So when I do sign test, it'll be easy with the exponential part. The 1 minus x part can be 0. At x equals 1, it's 0. And we would have the derivative 0 at x equals 1 because that factor is 0. And that's the end of the story because that exponential function is always positive. No critical points from it. Let's take a second derivative. Okay, it's split up along this line, but it's another product rule with a chain rule inside it. Looks like just once. Calculate the derivative. We'll get this quantity here. Okay, is this ever 0? Yeah, when the 2 minus x is 0. So x equals 2 is a potential point of inflection. Stuff over here, never 0. Domain of the function, all real numbers. And the domain of the derivative and the second derivative is all real numbers as well. There's no division by 0 or weirdness going on. But there are places where some things are 0, where the derivative is 0, x equals 1, and the second derivative is 0, x equals 2. So let's take the domain of the function, negative infinity to infinity, and let's remove that critical point of 1 and that potential point of inflection at 2. From those intervals, choose a test value. Plug it into the derivative. Derivative is sitting right here. Plug it into the second derivative. Second derivative is sitting right here. Produce values, if you like. It's really just the signs of those values I'm interested in, and the exponential functions will always be positive. So I know the signs of those. But here's the values produced. For the derivative, we get positive, negative, negative. So for the function, we get increasing, decreasing, decreasing, as usual. Plug those values into the second derivative. It produces negative, negative, positive, giving us for the second derivative, concave down, switches to concave up. Any observations here at 2? Change concavity really is a point of inflection, not just a potential point of inflection. I leave it to you to pause the video and check the numbers in the table and convince yourself that I've got the signs correct. The sign is the most important part. The value is irrelevant. I want to get them right. But it's the signs, the plus and minusness, that matter. So that gives us this information. Here it is in an abbreviated table. So there's the increasing and decreasing in the concavity information. How about extrema? Well, let's see. Function increases and then decreases. So at critical point 1, it must have a local maximum. Local maximum at x equals 1. Plug 1 into the function. You get e to the negative 1 out. 1 over e. It's about a third. So that must be a local maximum. We see that this point, 2, f of 2, really is a point of inflection. So that's expressed down here. I plug 2 into the function. We get out 2e to the negative 2. That's about 2/9 or so. It's less. So point of inflection. We'll plot those 2 points. My scale, I don't know, it's probably not very good. If this is 1 unit, remember 1 over e, that's about a third of a unit. So my aspect ratio is all out of whack. If you're used to dealing with that with the televisions. Yeah, I've really stretched the y-axis so you can see it. So my scale's off. It's the shape that matters, but it is vertically stretched, not to scale. Plug in 1, we get out e to the negative 1. Plug in 2, you get out that thing, which is smaller. Intercepts, we had x e to the negative x. X equals 0 will produce an intercept. Let's plot that as well. That'll become part of our routine when we deal with more specific steps. The derivative was 0 at 1, so a little red mark. Change concavity at 2, a little X mark, and then it's off to use this information here. I want to add one other observation, more foreshadowing than relevance here, because I don't think we know how to do this. I don't think we know how to do this with our current information. We will in the next section. The limit as x approaches positive infinity of x e to the negative x is 0. This thing has a horizontal asymptote off to the right because of this particular limit. It doesn't have a horizontal asymptote off to the left. But it does have a horizontal asymptote. I want a nice graph. Let me add that piece of information as given. That we're not equipped to do just yet, but it's true. So with that information, let's go through and graph something that is increasing, concave down. Okay, up to 1, I want increasing and concave down, pass through that point, increasing, concave down, level off because of the little hash mark at the critical point. Now from 1 to 2, I want it to change to decreasing and concave down. Okay, so it'll change over to decreasing and concave down to here, where it's going to change concavity because of the x and be decreasing and concave up. So it's decreasing and concave up. If I use my horizontal asymptote information, I'd level it off. If I didn't have that information, I might think maybe it does something like this. You know, it continues to go downhill and it continues to arch upward. It can't go down here though, because that function is only 0 when x equals 0. So I've got concave down and decreasing. Oh, it had to have a horizontal asymptote of something because it can never reach 0. It didn't necessarily, those given that information, have to be the x-axis. It turns out it is, though. It could have leveled off earlier, for all I know. But with this extra information, I know where it levels off at the x-axis. So the graph of this function looks something like that. And I can't really play much in the way of how do you know it doesn't games with you, because when you know a lot about this function, you know the increasingness, the decreasingness. The only thing I can think of is to ask you, well, how steep is it over here? I mean, do I draw it really, really steep or what? Well, it depends on the derivative. I guess that kind of information I can't really answer without looking at the derivatives, the values of the derivative, or looking at plotting more points. That we're not interested in. We're interested in this general shape, and this is a pretty good idea, the shape of this graph. Back to the notes, and a 7-step procedure. We'll illustrate that with several examples. A bit lengthy for a test question because there's so many pieces. Arguably a good question for a good procedure for a couple of questions. So the procedure for graphing y equals f of x spelled out in these steps, we'll follow these steps in the examples, is step 1. Identify the domain of f and any symmetries the curve may have. We haven't spent a whole lot of time talking about symmetries. It's in some of the review material. Find the derivative and the second derivative. Find the critical points. Identify the function's behavior at those critical points. That is the derivative 0? And that's why we're dealing with a critical point? If so, little horizontal hash mark. Or is the derivative undefined and something's gone wrong? Well, in that case, I say little vertical hash mark for those kinds of critical points. Find where the curve is increasing and decreasing. Okay, we'll take care of that with a table. Next, repeat the previous 2 steps, but for the second derivative. Find the points of inflection, if any, and determine the concavity. So find potential points of inflection, make a table, then you can find points of inflection. So steps 3, 4, and step 5, very, very similar. Identify any asymptotes. Okay, we'll do some of those where we actually compute the asymptotes here shortly. We've dealt with asymptotes back in chapter 2. It was the last section of chapter 2. Plot key points, special points, intercepts, we've been doing that, and these other points that you found, the critical points and the points of inflection. So there's the 7 steps. Let me encourage you to read that extremely expensive book. There's lots of good examples in the book of graphing and following these steps. I've intentionally done none of the examples in the book. I've just worked exercises. All right, so speaking of, let's do more. Okay, let y equals f of x be a continuous function, and let its derivative be y prime of t, so because I meant y equals f of t. A little typo, that should be a t, so we're using t for the variable. Y prime of t equals sine t. T is in the interval from 0 to 2 pi. So they didn't tell us a function, they told us its derivative. Find y prime, use steps 2 through 4. Okay, so I think we won't look at, this is the instructions the book gave us, so we're pushing first derivative information in this one. Step 5 was the concavity stuff. They want the second derivative, so fine. And the graphing procedure to sketch the general shape of the graph of f. General shape. Yeah, you don't know what the function is, so I can't really plot any particular points. Indicate, where the derivative is 0 with the horizontal hash marks. And I put X's if they had us look at concavity, but they haven't with what they asked. First 4 steps don't address concavity. Okay, y prime equals the sign. They wanted the second derivative. I differentiate the sign. I get cosine. There's the second derivative, though we're not going to use it. Step 2 was to find y prime and y double prime. So we have those already. Step 3, critical points in the interval 0 to 2 pi. So we've got the derivative is sine t. Where's the sine function 0? At integer multiples of pi. So it's 0, at pi, at 2 pi, at 3 pi, at 4 pi, at 5 pi, at negative pi, negative 2 pi, negative 3 pi. But only 3 of those are in this interval. So 0, pi, and 2 pi are in this interval. So these are the critical points of this function because the derivative is 0 there. So I'd plot points. Only thing is they didn't tell me what the function is. I'd plot points and put little hash marks through these 3 points, indicating horizontal tangent lines. Step 4, ask about increasing and decreasing. Okay, we got the derivative. Easy enough. We'll take the domain of the function, 0 to 2 pi. We'll remove the critical points, 0, pi, and 2 pi. So we lost the endpoints and we lost the center point, producing these 2 open intervals. We'll pick a value, any value, in those intervals. Pi fourths, 5 pi fourths. Pi halves and 3 pi halves would be maybe even more reasonable. But anything, any special angle in here, so you know what the values are. So when we plug those values into the derivative, into the sine function, produces positive square root of 2 over 2, positive. And over here, negative square root of 2 over 2, negative. Increasing here, decreasing there. So there's the 4 steps. They want us to graph. I can't plot specific points because they didn't tell me the function. What I know, this function increases, then it decreases, and I know some things about it leveling off. All right, increases, then decreases, and levels off. 0, pi, and 2 pi, some things happen. So I'll plot some points, say here, here, and here. I expect that to be a periodic function. Suspect is all I've got at this stage, though, because the derivative is a sine function. So I suspect it's got something to do with some cosine functions. Derivative of cosine is negative sine. It's got something to do with a cosine function. But I plot 3 points and put the hash marks there. I put these 2 points at the same elevation, same y value. I can't really justify that. I got my suspicions, but I can't really justify putting those at the same level. I couldn't argue against you dropping this one down lower. I do know it increases and then it decreases. So what we get is comes out of here level, and then it increases, and then it levels off. Comes out of here level, it decreases, and then it levels off. That function has all the properties that we know. Could you find points of inflection? You could if you could find the second derivative. We did find the second derivative. Guess what? I bet you here at pi halves and 3 pi halves, I bet you it changes concavity right there. And we could establish that because we found the second derivative. We just didn't test it. And indeed it does. It changes concavity here and here. I didn't put red X's there because they didn't ask me about it. Let's do another one with all the red X's and everything. All right, graph the rational function y equals f of x is x squared minus 4 over x squared minus 2. Use all the steps, hash marks and X's. Okay, so we're throwing everything at this one. First, domain. The only thing that could go wrong is division by 0, and that happens when x is plus or minus the square root of 2. So the domain of the function is, this was step 1, the whole real line with negative square root of 2 and positive square root of 2 removed. When we make the tables, we take the domain of the function, this, and we remove critical points. So next we'll find critical points, and we'll further subdivide this if necessary. Oh, they ask us about symmetries. If I replace x with negative x, and I get the same value of the function back out, it's an even function. You do because of these exponents of 2. If I replace x with negative x in the function, I get the same function out that we started with. Such a thing as an even function. It absorbs negative signs. Yeah, of course it does because of the squares. That tells you we've got symmetry with respect to the y-axis. Not real hung up on the symmetry stuff. It has its time and place. Its time and place is pre-calculus as far as classwork goes. We got other stuff on our mind. But I bet you when we're done, we got a graph that's symmetric with respect to the y-axis. Derivative. Okay. We had x squared minus 4 divided by x squared minus 2, right? Go back. We had x squared minus 4 over x squared minus 2. Yeah. So quotient rule for the derivative, be derivative of the numerator times the denominator minus the derivative minus the numerator times the derivative of the denominator, be the quotient rule. So we got the derivative of the numerator, that was the x squared minus 4, here it is over here, is 2x, times the denominator, minus the numerator, x squared minus 4, times the derivative of the denominator, derivative of x squared minus 2, is 2x over the denominator squared. Simplify, we get this. Simplify the numerator, you'll get this. Second derivative, let's take the derivative of the first derivative. Derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. Little chain rule stuff because the denominator is the composition of functions. The squaring function has something inside it. We differentiated the squaring function. Chain rule sticks the derivative of the inner function on there. Do your thing and simplify. So let me skip the algebra on that. And here's what we get for y double prime. So derivative, first derivative, second derivative. All right, how are we doing on critical points? Consider this. What are the critical points? This is 0 when x equals 0. 0 is the only critical point. What's up with a plus or minus the square root of 2? Because the derivative doesn't exist there. Yeah, the function doesn't exist there either. So they don't count as critical points. They're important points when we make a graph, a chart, when we make a table, those points will be removed. They're not even in the domain of the function. So they don't count as critical points because they're not in the domain of the function. They're important points. They're not called critical points. So let's see, we get f prime of 0 equals 0. We'll make a little hash mark at x equals 0. And that's the only critical point. Plug 0 in, we get 2 out. So we got the point 0, comma 2. It'll get a little horizontal hash mark when we graph it. Increasing, decreasing information. Okay, here's the domain with that critical point of 0 removed. I'll take test values from each of those intervals, nice little numbers. I'll plug those test values into the derivative, and out will come positives or negatives as given. The denominator, the derivative, involves the squaring. Let me go back and look at the derivative one more time. So all this won't fit on single slides. Here's the derivative. That denominator squared. It won't be 0 because we won't let it. And it'll always be positive. Denominator is positive. The sign of the derivative is determined by x. It's determined by the numerator. So we've got positive denominators throughout. Numerator is -8, -4, some negative derivatives. +4 and +8. Symmetry is not a coincidence. We've seen some symmetries, haven't we? So we get these signs for the derivative and these corresponding increasing, decreasing information. Functions decreasing on the union of these two intervals. It's increasing on the union of those two intervals. There's where it's increasing and decreasing. How about concavity? Well, there's the second derivative. It has no potential points of inflection. Telling me this is never 0, right? Numerator's never 0. Here we've got 3 times x squared. That's something positive, plus 2. But numerator, the 3x squared plus 2 part, That's never 0. That's always positive. So it doesn't have any any potential points of inflection where the second derivative is 0. How about where the second derivative is undefined? Well, yeah, plus or minus the square root of 2 are causing a problem, but they were causing a problem from the beginning, so they don't count as potential points of inflection. It's got no potential points of inflection. Could it still change concavity? Yeah, just it'd have to be at a point that's not in the domain of the function. So we still got to make a table. Okay, so here's a table. We've taken the domain and removed, we didn't remove anything because we didn't have any potential points of inflection. So we've taken the domain, which is not a connected set. So I do have to check each of these intervals. Take a test value, -2, 0, and 2. I expect some symmetry from that. Plug those into the second derivative. Here's the values that come out. And look, we got the same thing at 2 as we got at -2 for the second derivative. That's that symmetry stuff. Negative, positive, negative, giving us concave down, concave up, concave down. Here's a set on which we have concave up. Here's a set on which we have concave down. Part 6 said, check for asymptotes. Okay, we hadn't done this in a while. Take a limit as x approaches plus or minus infinity for the function, looking for horizontal asymptotes. How do we deal with these? Divided numerator and denominator by highest power of x in the denominator. That's x squared, so I'm multiplying by 1 over x squared divided by 1 over x squared. Just multiplying by 1. Distributing, simplifying, using properties of limits. What do you know about limits as x approaches plus or minus infinity? Not a whole lot, but I know 1 over x goes to 0. So we get zeros from these two limits. So we get 0 squared, if you like. And that limit's 1. So y equals 1 is a horizontal asymptote. You buy that? Here's a function. Oh, sure, when x is really big, this is close to 1. Numerator and denominator about the same size. So yeah, y equals 1 is a horizontal asymptote. How about vertical asymptotes? Boy, well, it's going to have 2 of those. Here's the original function. Factor that denominator. Factors to x plus the square root of 2 times x minus the square root of 2. Treated as the difference of 2 perfect squares. Though the square root of 2 squared, maybe you don't think of that as a perfect square. But 2 is the square root of 2 squared. So I can factor it like this. I want to see factors so I can test signs. SIGN signs. Dr. Bob's infinite limits theorem says, hey, you got an irrational function, you got a place where the denominator is 0 and the numerator isn't. That implies one-sided limits are positive or negative infinity. I don't know which is what. We're going to have to check 4 different things. But Dr. Bob's infinite limits theorem says you got yourself some infinite limits here. So you've got yourself some vertical asymptotes at both 2, square root of 2 and negative square root of 2. Does the function go to positive infinity or negative infinity? Let's find out. So this is a bit of review. This is also a little bit redundant because we know where this function is increasing and decreasing. We found that information a couple of slides ago. But let's go back and do this the way we did in section 2.7, I think it was. I think it was the last section of chapter 2. I know we're getting infinite limits out. So let's consider first, the limit as x approaches negative square root of 2 from the negative side. That is, x is close to negative square root of 2 and on the negative side, less than negative square root of 2. So what's the resulting sign? I call these sign diagrams when I did this in the past. What's the sign of the function? Close to negative square root of 2. Well, the numerator is close to negative square root of 2 squared is 2. 2 minus 4. Numerator is close to negative 2. Oh, that's negative. How about this expression? We're close to negative square root of 2. Then this is going to be close to negative 2 times the square root of 2. I mean, I'll have negative square root of 2 minus another square root of 2. That'll be negative. Those two are easy. This is a tricky one. And this is the one that's affected by the one-sided limit. X is close to negative square root of 2. Then this is close to 0. Yeah, close to 0 and positive or negative? Well, close to negative 2 and less than negative 2. So I've got something less than negative square root of 2. I add square root of 2 to that. There's a little bit of that negative left over. And the sign of that factor is negative. We've got 3 negatives, a numerator and 2 in the denominator, yielding a net negative, odd number of negatives. What's that tell you? The limit as x approaches negative square root of 2 from the negative side is negative infinity. Yeah, that one-sided limit is negative infinity. If we approach negative 2, square root of 2 from the positive side, similar analysis, we get this factor to change from negative to positive. X is close to negative square root of 2 and a little bit bigger than negative square root of 2. You add square root of 2 to that, and it's the positive square root of 2 that dominates, and there's a little positive bit left over, as we did in chapter 2. Now we've got a positive and 2 negatives for a net result of a positive, and that one-sided limit as x approaches negative square root of 2 from the positive side, that one's positive infinity. And a similar analysis gives what the behavior at positive square root of 2 from the negative side and the positive side. So we get these two asymptotes behaving differently from the left and the right. Is it time to graph? Yeah, so let's graph it. All right. We had the concavity information, we had the increasing, decreasing information, we had the horizontal asymptote information, we had the vertical asymptote information. All right. Here's what I do. First, I'll find the intercepts. X equals plus or minus 2. X equals plus or minus 2 gives x-intercepts where the function is 0. I plug 0 in, I get out 2. That gives the y-intercept. We had 0 as a critical point. So I'd have now the 3 blue lines, put a little horizontal hash mark through there because the derivative was 0 there. And that was it. Points of inflection, there weren't any. I don't have a point I can put a red X through. It doesn't have points of inflection. Though it does change concavity, but it does it at points that aren't in the domain of the function. So they don't count as points of inflection. It changes concavity, in fact, at plus or minus the square root of 2. Concave down to concave up to concave down. I'll graph the vertical asymptotes. We know those occur at negatives, plus or minus the square root of 2, positive square root of 2, and negative square root of 2. Horizontal asymptote of y equals 1. So thirdly, I'll draw that. So the way you would do this dynamically is first plot those 3 points. Secondly, plot the information in red, the hash mark indicating the derivative, the horizontal asymptote, and the 2 vertical asymptotes. Next, decreasing concave down. So I want horizontal asymptote, so we'd have to come in something like this. I want the thing decreasing, pass through this point, nothing special about that point other than it's an intercept. Keeping the concave down and decreasing this, and having now that vertical asymptote. So it'd have to look something like that. Between negative square root of 2 and 0, I want decreasing concave up, vertical asymptote. So we'd have to come down like this, decreasing, concave up. They have to level off here because of the critical point. Comes out of here level. 0 to the square root of 2, changes to increasing and concave up. So remains concave up, but changes to increasing, and it's got the vertical asymptote. Have to do something like that. Finally, on the right-handmost piece, increasing, concave down, vertical asymptote here, have to be increasing, concave down, pass through this point because it's an intercept, remain increasing, concave down, and respect the horizontal asymptote. That function looks a lot like that. We didn't use that information on the previous slide directly. I got all the information from what's in front of us. But notice, indeed, as x approaches negative square root of 2 from the negative side, function goes to negative infinity. As x approaches negative square root of 2 from the positive side, function goes to positive infinity. As I commented then, we can actually determine how it behaves at those asymptotes from the increasing, decreasing information. So there was some redundancy in there. One parting comment about this one. It is symmetric with respect to the y-axis, and we observed that early on as well. Yeah, it's a mirror image of itself about the y-axis. as predicted. That's what that function looks like. We know asymptotes. We know a bunch of stuff about that function. It looks like that. So I'm quite confident in the shape of this one. A handful more of these things. Number 122, actually a little bit easier, says find the coordinates of the vertex of the parabola y equals ax squared plus bx plus c, where a is non-zero. Where's the parabola concave up, concave down, and explain your answers. Okay, vertex of a parabola. Well, we'll differentiate, take first and second derivatives. They ask us about concavity in part B. Vertex of the parabola is an absolute extremum of that function. It's a maximum or a minimum that depends on the A, B, and C parameters. Well, let's find the critical points. F prime of x is 2ax plus b. Differentiate, bring the 2 down, lose the x, the constant's gone. So we get 2ax plus b, differentiating with respect to x, of course. 2ax plus b is what we get for the derivative. So the second derivative is just 2a. Where are the critical points? Take that second derivative, set it equal to 0, solve for x. So solve the little equation, 2ax plus b equals 0. X equals negative b over 2a. Sounds familiar? Reminds me of the quadratic equation. Not a coincidence. There's what we get for the critical point. Let's plug that critical point back into the function. It'll produce this value, negative b squared plus 4ac divided by 4a. That reminds me a little bit of the quadratic equation as well, a little less so. But the vertex will be at the critical point. Here's the critical point. There's the x value. There's the y value. So that's the coordinates of the the coordinates of the vertex. It is the critical point, treating that as a function. Does it correspond to a max or a min? Well, that depends on some other stuff. We'll be able to tell actually from the second derivative. Is a function concave up, smiley face, or concave down, frowny face? But they wanted the vertex. It occurs at the critical point. There's your critical point. Next, they want us to discuss concavity. We got the second derivative right there. Ooh, the second derivative is a constant. Is this positive or negative? Well, it depends on the sign of A. Second derivative is 2A. Second derivative test for concavity says then the parabola is concave up if that's positive. That's positive if A is positive. So we get concave up when A is greater than 0, concave down when A is less than 0, A being some given number. I mean, they didn't give it to us specifically, but the concavity depends on the sign of the leading coefficient. And you knew that from your algebra experience. So calculus is, in fact, consistent with algebra. Concavity is determined by the leading coefficient. Just a quick observation. Geez, so it's either always concave up or it's always concave down. So there is no point of inflection, right? That's how parabolas behave. No points of inflection. Second derivative is a constant. And we were told A was not 0, or else we're not talking about parabolas, we're talking about lines. And some of these computations are incorrect. But A is not 0, so we're good. Cubics. Okay, just do a similar type thing. Ax cubed plus bx squared plus cx plus d. A is not 0. It really is a legitimate cubic polynomial. What can you say about the inflection points? Okay, better find the second derivative. Easy enough. It's polynomial. Take the first derivative, we get this. Take the second derivative, we get second derivative is 6ax plus 2b. You want to know about concavity? Well, then let's find where the second derivative is 0 or undefined. It's always defined. I'm dealing with a polynomial here. Could be 0 though. Set this equal to 0, solve for x. We'll get negative 2b divided by 6a. That simplifies to negative b over 3a. So second derivative evaluated at negative b divided by 3a will be 0. So this is a potential point of inflection. I stopped italicizing a couple of problems ago. I can't call it a point of inflection unless it changes concavity. So we'll make a table. We'll take the domain of the function, the whole real line, and remove that potential point of inflection, negative b over 3a. We'll pick test values. Okay, I want something less than negative b over 3a. How about negative b over 3a minus 1? That's less. We're on a test value over here that's bigger than negative b over 3a. How about negative b over 3a plus 1? They're in these intervals. Let's use them for test values. And in fact, plugging them in, things simplify quite easily. We get that the second derivative is negative 6a in this interval and positive 6a on this interval. But a itself could be negative. So I can't put the concavity down here and complete this table unless I know something about a. I know a is non-zero. I do not know a is positive. I know a is non-zero. It's a typo there. I should read a is not equal to 0 by hypothesis. So we can see that indeed it does change from positive to negative or negative to positive. I can't tell which one because I don't know the sign of a. Bad typo here. This should read a is not equal to 0. That was the hypothesis. I'll get that modified and posted online. F changes concavity there. So we do have a point of inflection at this x value, negative b over 3a. So that's a point of inflection. Indeed, it changes concavity. I can't tell you if it's concave up here and concave down here, or concave down on this one and concave up on that one. I can't tell which is concave up and concave down unless you'll tell me more about a. Just telling me it ain't 0 doesn't cut it. I need to know if it's positive, in which case we've got concave down here because a is positive and concave up here because a is positive, or the other way around when a is negative. But I do know it changes concavity. You don't tell me much information. I'll do what I can with what you've told me. So there's only one inflection point. We can plug that negative b over 3a in, find the corresponding function value. Nothing pretty about this, but there's what you get out of the function. So what can you say about the inflection points? There's one, and that's it. I can't tell you about concavity unless you'll tell me about a, but I can tell you one point of inflection, and that's it. And excellent. So there's a pile of information on graphing. Let me emphasize again. Read the examples in the book. There's a whole bunch of examples in the book. They're good examples. I avoided doing them here. This idea of making tables persists from the previous section to this one. Make a table, get derivative information in the previous section, second derivative information in this section, or both information from both first and second derivative. We also did in this section. How do you graph a function? This is how you graph a function. You don't plot points willy-nilly. You plot points cleverly. And how you determine what the clever points to plot are is you find critical points, maybe intercepts, and you find points of inflection. Those are the important points. Don't plot functions by just plugging numbers in and getting numbers out and making a bunch of dots. Maybe you didn't pick the right dots. It's the first and second derivative. Those are the guys that tell you the points to plot. You plot those points and you use this additional information about increasing, decreasing, and concavity. That tells you what happens between those points you've plotted and allows you to connect the points together in an educated way. That's how you graph a function. So one of the big applications of Calculus 1 is this stuff involving graphing. And we'll take this and run with it and do some applications to extrema here in a section or two. Productive long day. Have a nice day. I will see you in the next section in time. Bye-bye.